Swayam Prabha, Digital India, Educated India.
Okay, so today's topic is bipolar junction transistor. All of you have learnt about the bipolar junction transistor in your basic electronics. We will learn little more than that in this course, because now we have a much broader background in terms of PN junction, metal semiconductor junction, and we have learned more theory of the semiconductor characteristic. So transistor, as you know, it is basically transfer resistance, right? So basically what you do, you control current flowing across two terminals using the third terminal, right? So your input is somewhere here and output is somewhere here. It's called bipolar transistor because both the polarity take part in the current conduction. Both the polarity means positive charge as well as negative charge. So negative charge, of course, we call electron, positive charge we call holes. Now this is a concept basically, but it appears that the current is carried by the positive charge carriers or negative charge carriers through the Hall experiment, and we have already learned about the Hall measurement. Now there are various types of transistors or switches. You have BJT here, you have MOSFET, and then there is another application of this PN junction is the laser, basically to emit the light. So in this case, when carriers combine, they emit a photon corresponding to the band gap. In case of bipolar transistors, both the carriers take part. In case of MOSFET, it's called metal oxide semiconductor field effect transistor. So it's field effect basically. So when you apply a voltage at the metal, some field is created, and that basically control this channel and the current flows. It's basically like a tape, right? Where the flow of water can be controlled by turning this knob clockwise or anti-clockwise. Or you can see dam, right? Where you open the gate, the water flows. So today's topic is basically bipolar junction transistor. So here you have seen this emitter, base, and collector. So their names basically have a reason from some historic account. Emitter is basically it's a source basically, right, which emit the carriers which are responsible for current flow. Base is basically a mechanical support, right? But how do you see it as a mechanical support? It basically, if you recall, in 1947, right, the first transistor that was fabricated, it was a point contact transistor, right, where this germanium was a base, right, on which two metal leads were connected, and that became a transistor, right? So this was a base basically on which these two leads were connected. So that's why it is carrying that name, the base. But later on, with technological advances, modifications, we have a narrower base here, because the original transistor that was accidentally invented, it has not the fantastic characteristic, right? So later we realize, what should be the design specification for the base. So this middle region is called base, and then of course, as the name collector is basically collects the carrier that is injected by the emitter. So emitter will inject the carriers, and they will pass through the base, and these carriers will be collected by the collector. So that's why these three terminals have their different names. Now to understand operation of BJT, let us recall the PN junction. Now we have learned that PN junction can be forward bias or it can be reverse bias, right? In case of forward bias, these carriers are injected, right? And this depletion width is reduced. In case of reverse bias, depletion width is extended and these carriers are extracted or depleted. The minority carriers, and these are minority carriers. And of course, the IV characteristic in forward bias, it increases exponentially. Then due to other effects, it tend to saturate. In reverse bias, it's almost negligible reverse saturation current, and then until it breaks down. So now what will happen if you bring these two junctions together? Before that, let us look at the reverse bias more carefully. In the reverse bias, what is happening? There is a field here. The field is such, from N type, it will extract holes, right? So holes will move from N to P. Now, so if you look at the IV characteristic for the reverse bias, right? You have a constant saturation current is flowing. Now somehow, if we can create the holes here and electrons here, let's say we shine the light, we have some optical generation. How this characteristic will change? You have some light is shining on it. How this characteristic will change? Let's say due to this optical, the generation rate is G optical, right? And then the delta N or delta P will be G optical times tau N or tau P. So this will be extra carriers, right? So your N and P naught will be N naught plus delta N, P will be P naught plus delta P, right? So how this characteristic will change? This current will increase. If you increase the intensity, this current will increase, correct? So this is due to the generation, but generation is not controllable. Basically, you are signing the sample together, and if you want to just focus on particular side, it will be little difficult. You can use another technique. If you supply the holes here from some other method, and that you can do when you connect these two together, right? If you connect these two together and you forward bias it, then it will inject holes here, and these holes will be swept away by this reverse bias junction, and in that case also you will have similar effect. So all the reverse bias, you will have large current, right? So let us see how it works. So these are the two PN junction, and we are going to join them. And when we join them, what will happen? Holes from P region that is injected by the forward bias will be swept away across the reverse bias junction. So the first junction is forward bias, second junction is reverse bias. So although it is reverse bias, you will have current here. Now if the base length is large, then by the time they reach here, all would have recombined. If base is short, then a significant number of holes will reach the other end, and where they will be swept away by the reverse bias field. So we will have large current. So that's why there is a requirement that the base width usually kept narrow, and narrow compared to the diffusion length of the carriers that are injected. Okay, so here you see the movement here, then they are swept away by the reverse bias junction, and these holes will move to the other side. Okay. Now When this base emitter junction, we call it emitter, base and collector. When base emitter junction is forward bias, then it is not only the holes will move from P to N, electrons will also move from N to P. Right? So for a better transistor action, we will prefer that this current is mostly composed of holes from P side, right? So we will use P plus junction or higher doping on emitter compared to the base. So the hole moving from P to N will be more, electron moving from base to emitter will be less. And if these holes to be removed faster, we will try to increase this voltage, right? So now they will be removed only if they come here, right? And these holes can come here faster if this width is reduced. So let's define the notion for the currents, right? Now for emitter current is, now here we are dealing with PNP transistor, right? This is a PNP transistor. So emitter current is defined as a current entering the emitter terminal, and collector current is defined as current leaving the collector terminal, and base current is defined as current leaving the base terminal, and you can write IE is equal to IB plus IC. Similarly for NPN, you can define other way around. Because see here holes are moving, right? So either you define other way or they will just all the currents will carry negative sign. So by the Kirchhoff current law, assuming there is no accumulation there, you will have emitter current will be the sum of collector current and base current. And VEB is forward bias, VBC is reverse bias, right? And your VEC will be VEB plus VBC. That is Kirchhoff voltage law. So these are the basic relation that will keep in mind. Okay. Now, if you see the typical IC versus VEC curve, right? You can find few regions there: a saturation region, right? A linear region, a cutoff region. When we are using it as amplifier, we usually work in this linear region or forward active mode, and of course cutoff is when both the junctions are reverse biased, and saturation when both the junctions are forward biased. So when both the junctions are forward biased, then because this emitter is highly doped, so the voltage across base emitter will be slightly more than the voltage across base collector. So your VEB is slightly greater than VCB, or you can say minus VBC, right? And that means your VEC will be small. You might recall 0.2 or 0.3 that we assumed in the basic electronics. And of course your IE is more than IC, and IB is non-zero. So this is a saturation mode. Now in saturation mode, what happens actually? Due to this base collector being slightly forward bias, it is not able to pull away all the carriers. So collector current is not beta times IB basically. It is less than beta times IB. Then in linear region, of course, VEB and VBC, they are both are greater than 0, and VEC is quite large. and IE and IC both are positive. That means IB is also positive because IE is greater than IC. Now if you see here, with respect to base current, if you increase the base current slightly, your collector current increases significantly. That means it can be used for amplification. So for a small change in base current, you will have large change in collector current. In case of cutoff, both the junction are reverse biased. So VEB is negative and VBC is positive. So that means VEC is positive. That is basically your IE is negative and IC will be positive. And IB will also be positive but small. So this all I think you have known it. So just to review it, we are discussing, and let us see inside what exactly happens. Now with this understanding of BJT, you might have discussed different configurations, right? So you can bias this BJT as common base, common emitter, or common collector. Those you can see the summary here. In common base, your input is between base and emitter. Output is across base and collector. In common emitter, your input is across base and emitter. Output is across collector and emitter, right? And this is used for basically gain, right? Now why it is used for gain? Because a small change in base will change the uh, collector current significantly. Now another important factor is that your VEC can change over large value without affecting IC, right? So that means if you connect a load here, then if IC increases, the drop across RL will increase, and of course your VEC will decrease, right? But that will not affect the IC. So that means you have a kind of a current source which is independent of output voltage. So it's like ideal current source, right? So basically it's a basically base current controlled a current source. Then you have common collector. In common collector, input is across base and output is at the emitter. So VEC is the output, VCB is the input. Now common collector has other application where you need large bandwidth, all those properties. So this is also one of the configuration. Now when we discuss about BJT fabrication, we have already discussed about the fabrication while discussing the PN junction. So all those steps are followed in BJT fabrication. So what is typically done? If you look here carefully, these are typical dimension of transistors. This height is only 5 micron, right? And if you see here, this is emitter. Emitter is so small, right? Emitter is very small, and the base is order of micron or less. Now, if you compare this with the diffuser length in silicon, which is order of few micron, so this width is much less than the diffusion length. And this base can be narrower also. Of course, there will be some limitation how narrow we can make it. The base width has to be optimized. And then how it is fabricated basically on a substrate. You have basically bare layer, the bare layer, and then in that you have P plus contact for emitter, N plus contact for base in N well. This is N well, and then of course N well is made in P because we don't want any other PN junction to be forward bias. So this will take care of the isolation thing. And isolation can also be achieved through the oxidation. Okay, so and here is another slight variation of this thing. Here we have N plus buried layer. So this is basically to improve the conductivity of collector, because collector is usually less doped. So we have a N plus layer slightly away from the junction, so that it improves the connectivity of the collector. Now let us look at the device itself, how it functions. We have drawn this cartoon here for emitter, base and collector. Now base emitter is forward bias, so the depletion width is less here. Base collector is reverse bias, so you have a larger depletion width here. Now if we draw this in equilibrium, then all the Fermi levels will be aligned. So this is P type, Fermi level is close to valence band S, EV. This is N type, Fermi level is close to EC, and this is again P type, Fermi level is close to EV. And then of course emitter doping is higher, so this is Fermi level is closer to EV, so the gap is small. It is slightly less, it is also less, so they're slightly away from this one. Now if you see here, for holes, this is the barrier, but once these holes are injected, they can glide down the barrier. And you can notice one more thing, this band structure is the energy, right? So it is minus Q times V. So potential will have opposite of this thing, right? So it's decreasing, so it will increase here, then it's increasing, so it will decrease here. So your potential is increasing from emitter to base and decreasing from base to collector. So you have this potential barrier here, and the carriers will glide here. So this is basically the like basic PN junction only. And then you can let us try the drawing. This is for PNP. You can try the band diagram for NPN. Please try it now. Take a minute and draw the band diagram for NPN VJT. So N will be here. P will be here. N will be here. Now you can draw the potential also. It should be inverted of this thing. Now what about the charge? So can you show the fixed charge also? So for base emitter, of course the depletion width will be narrow, but there will be some depletion width here, and it will mostly extend to the base side. Why? Because base is less doped, emitter is highly doped. And in case of base collector doping is even less, so this depletion will extend to the collector side. And then of course it is P type, so the charge is negative. It is N type, charge is positive, this P type, so charge is negative. So this is all fixed charge, right? And they will have the electric field. So you can see what is the direction of electric field. positive charge to negative charge. What is the direction of electric field at the base emitter junction? Positive charge to negative charge. So the field is negative here, field is positive here. Positive means it's plus x direction, negative means it's minus x direction. Now, if this BJT is in active bias, so in active bias basically your base emitter junction is forward bias and base collector junction is reverse bias, right? So in active bias, what will happen? When you forward bias it, what will happen? This will go up, right? Fermi level will be shifted like this, and this will be reverse bias, right? So this gap will even increase, right? So you can see here. So this is emitter voltage, right? VB, and this is base collector voltage, right? Base emitter is forward bias. That means this is PNP transistor, PNP, right? So this is positive bias, this is negative bias, right? So that's why Fermi level goes up. Base collector is reverse bias, so that means this is positive, this is negative. So compared to this one, it goes down, and this is negative, it goes up. So where this barrier is reduced, so hole can easily cross over this one, and they can easily glide down. An electron, of course, they can glide down here, but they are minority carriers here. And once they glide down, they will have same ease of crossing over as the holes from emitter. So in this case, most of the current will be controlled by the holes, because holes are in majority in the emitter. So once these holes are injected, they are swept away by the electric field here. Now, as long as this junction is reverse bias, these holes will be swept away, regardless of the voltage. And of course, for higher voltage, there will be other changes, like this depletion will slightly change, right? They will be swept faster, but that will of course depend on the number of holes that are coming from emitter to the base junction. Then there are different factors that are responsible. So if you look at the emitter current consists of the hole injection from emitter to base and electron from base to emitter. That will emitter current. What about the base current? Base current will consist of course, these electrons injecting from the base to emitter, number one. Number two, these holes are getting injected here. So these holes and electron, they are kind of, they are in abundance here, so they will recombine. So these holes, minority carrier, their concentration is more in n-type base, so there will be significant recombination. So recombination will usually dominate the base current. And another a small component to the base current can be the reverse bias saturation current from base collector junction. And of course, if you make the base thin and dope it less, we can reduce the base current, because for thin base, these carriers will spend a smaller time there, so their recombination probability will be less. Okay. Now there are different parameters for. Okay, you see the doping here. This is the collector doping, right? Now there is a basically I will answer your question. There are two contradicting requirements. If you consider the base here, right, and this is your collector, right? Now we want to achieve two things. Let's say if your collector is highly doped, right? Then what will happen? Your depletion width will extend inside the base, correct?
Yes, sir.
And if it extend inside the base, what will happen? There is a possibility that these two depletion widths may merge, and then the base action will be gone basically. these electrons, the holes, the carrier from the emitter will directly go to the collector. So we try to avoid that. Now what you might remember is that collector is highly doped here. You understand? Slightly away from the junction. And that is required to reduce the resistance of the collector. You understand? So collector is highly doped, but slightly away from the junction. So that is basically depends on the requirement. So depending on the requirement, you can basically. So if you apply, you are right. Basically, if you apply the voltage in certain range, then of course you can dope collector higher also near the junction. But then of course you see, for if the base width is fairly large, then you don't have to worry about it. Especially for the very narrow base, you have to worry about it. There is no universal rule like this.
Okay. Okay, thank you, sir.
Okay. What you can say, maybe in your textbook also there is some doping diagram is there. Let me see. This is shown here. Where it is shown. Maybe what I will do, I will share some of the recent devices that are being used to make the this BJT, and what is the typical doping profile there. So maybe you can search some data sheets for BJT also. Okay, if they provide the doping profile there.
Okay.
Yeah, but you are right. You may find both the things there, because base collector is always a trade-off. Now sometimes what is done in base, people use a graded doping in the base. Now graded doping in the base is used basically to create a field. Now this field will accelerate the injected carriers. Correct. And when these carriers are injected, your performance of BJT will be better, because they will spend less time in the base. So transit time is higher. That means you can operate at a higher frequency.
Yes.
So all these doping factors are played with base and emitter.
Okay.
And in emitter also there are different considerations. So sometimes you can consider emitter to be wide, because emitter is highly doped. So the diffusion length will be less.
Yes.
So even a thin emitter can be considered thick, because doping length is less. Sorry, yes. Diffusion length is less due to high doping. Then sometimes people use polysilicon emitter. So that has another purpose basically, because we want to reduce the current or the carriers injected from the base to emitter. So we want it to be have high slope. Sorry, less slope. Base is thin, of course, that it will have less time for recombination and
more current.
It will be better. But there is a requirement because there is a non-linear factor also called base width modulation. Like early effect, you know, right? So that is basically base width modulation. So all these factors have to be considered while designing the transistor. But let us go through them one by one.
Okay.
So for now, okay. So we were discussing here. Did we discuss this one? So now there are different parameters also. One is called emitter injection efficiency. Now emitter injection efficiency is basically the ratio of the emitter current due to carriers from emitter, right? So that is due to holes, or you can say IEP, divided by total emitter current. Now total emitter current will be emitter current due to holes plus emitter current due to electrons, right? So this emitter current due to holes is basically injected holes from emitter to collector. Emitter current due to electron is basically those electrons going from base to emitter, because the junction is forward bias. And the range of this emitter injection efficiency will be between 0 and 1. When emitter is highly doped, the injection efficiency will be close to 1. If due to some reason base is highly doped, then this will be close to 0. Correct? So of course in BJT we prefer this injection efficiency should be as close to 1 as possible. And that of course you can control if you dope the emitter highly. There are other technique also, just for your information I can tell you. Sometimes people use wide band gap emitters, right? So in wide band gap emitter, what happens? The barrier from emitter to base and from base to emitter, they are different because of this hetero structure, right? I think we have drawn one diagram also, Venn diagram for hetero structure. And here we are taking example of PNP BJT just for the simplicity, because the direction of hole flow is same as the direction of current flow. But NPN transistor is more popular because here the carriers are electron and they have higher mobility. So the popular transistor is NPN because of higher mobility of electron. Here we are discussing the PNP because the direction of current flow and direction of carrier flow is same. But their operation wise they are same. The theory wise they are both are same. So no difference is there. But this PNP is easier to understand. Otherwise, if I consider NPN, then the direction of carrier flow will be always opposite to the direction of current flow. So it may create some delay in understanding. Okay. So this heterojunction transistor is basically used to further boost up this injection efficiency. Let's say this electron see less barrier. Let's say carriers injected from emitter see less smaller barrier compared to the carriers injected from the base. Then of course this emitter injection efficiency will be close to 1. Once they are injected, they go through the base, right? In base, they recombine, right? So these holes are injected from emitter to base, and that current we call IEP. Then electrons are injected from base to emitter, we call it IEN. Now out of this IEP, some of them will recombine and most of them will go to the collector, and that current is called ICP. Then base collector junction is reverse bias, so there will be reverse saturation current due to minority carriers. So this electron moving from collector to emitter and holes moving from base to collector, they are reverse saturation current, right? So your base current is composed of these three component: IEN, recombination, and the reverse saturation component. And of course IC will be total ICP plus ICN. Now this is basically kind of minority carrier profile, right? So it's like a diffusion or carrier extraction. And the base transfer factor is called the ratio of the holes that are collected by the collector divided by the total number of holes that are injected by the emitter. So that is the base transport factor. So ICP by IEP. And of course, we also want this alpha to be alpha T to be as close to 1 as possible. So that means only factor that is stopping it is the recombination. So if somehow we can reduce the recombination, we can increase the lifetime. Two ways we can do it, right? We can reduce the width or we can increase the whole lifetime in the base region, right? To improve the base transport factor. Now, So we can write IC basically ICP plus ICN. Now usually ICN is quite small, so you can write ICP basically alpha T times IEP, and IEP is gamma times IE. So your ICP can be written as alpha T times gamma times IE, and this alpha T times gamma is called alpha, or common base current gain, right? This alpha is alpha T times gamma. So IC is alpha times IE, and then you have this ICN, right? So that contribute to this ICBO. Okay, now this is common ways in active bias. Then in case of can we relate this thing with this we have already written here, alpha T times, this alpha is alpha T times gamma, and this is basically ICN is ICBO. And similarly we can write the expression for common emitter current gain. Now common emitter current gain is related to is IC by IB, right? Or IC is written to beta times IB and some coefficient, right? So if you substitute here, if you recall this expression, IE is equal to IC plus IB, right? And you substitute it here, right? Then you can express the relations between IC and IB, right? So that will give you the common emitter current gain. So if you write it here, you can write IC is equal to beta times IB plus ICO, and these are related to alpha by beta is alpha over 1 minus alpha, right? Because if you see here, IC is alpha times IE is IB plus IC plus ICBO. So if you take the other side, so IC is alpha by 1 minus alpha, right? Okay. So this is alpha by 1 minus alpha is beta, and ICO is basically ICBO divided by 1 minus alpha, right? So if you have this is alpha by 1 minus alpha, this is will be 1 by 1 minus alpha, right? So ICO will be ICBO divided by 1 minus alpha, correct? So this is a brief review of BJT. Now what we will do, we will drive the current equation for BJT, right? So that will involve the solving of magnetic carrier diffusion equation. So we will take a 10 minutes break here, and then we will continue. Meanwhile, if you have a question, you can ask me.